Okay, well, I will stop about 10:45 to give you time for course evaluation. So we'll hand that out 15 minutes before the end of the class. So don't go away after I leave the class. I have posted 2 practice exams for midterms, last midterms from 2012 and 2013. So those are all good practice, I think, for next exam as well. So we'll see if we can take a look at that. What I didn't have much in the old practice exams is the very last part on more involved multi-rate, the QMF and the filter banks, polyphase. So we never really taught those things in the class in the past. So as some of you might have noticed, I threw out the analog filter design content to make room for more on multi-rate. So old exams will have quite a bit on analog filters. That certainly was not taught this time and will not be in your exam. So instead what I think we can do is maybe practice a few more problems beyond your homework today in class on the multi-rate ideas. So we'll try to see if I can complete a couple of problems from your textbook. So I didn't assign them as homework. We'll try to get to that. But before we do all of those, let me complete what I started last time. Also, I thought I would spend a little time on 2D FFT, but I think our time is better spent on my solving a few more problems on multi-rate rather than starting something brand new that I will not do justice to and will leave you with a lot more questions. Of course, it's good to leave you with questions, but instead of talking about that, I have given a great link to Professor Yao Wang's lecture at NYU that used to be called Polytechnic a couple of years ago. So you certainly can review those. Okay, so let's see where we are in the course Moodle site. This one is okay, so in fact, let's start with where I stopped. So okay, so last class we were talking about 4 different signals, and we saw that one of them, let's see. Okay, so this is where we were. Okay, so so we saw that the third one had the best, the third plot here had the best frequency resolution, but had the poorest time resolution because if you will notice the time sample 15 400, so the time was 400 milliseconds. So if we do a short time Fourier transform, at least in all the others, we will get a good time resolution because each time window is 200 milliseconds. So we will know what the frequency content is changing in 200 milliseconds. For the third one, the window length is 400. So the time resolution is going to be not very good. And that's in fact what we talked about. that the third sequence has better frequency resolution but worse time resolution. And so the window, I talked about how we multiply by Hamming window, similar to the window properties. So I had already defined some kind of a short time Fourier transform. Now we have to multiply by that window Wn, which is the Hamming window. And so this suggests that because we are multiplying by Hamming window, the short time Fourier transform is really the convolution of the window spectrum and the signal in that time window, and then we go back to the same kinds of properties as we looked at during FIR filter design and window functions. So again, how long the window should be, and we saw that having window length of 400 millisecond is not as good as 200 millisecond with respect to the time properties or the temporal resolution. So the length of the window determines the temporal resolution, because if you remember from all the window spectrums that we studied, the main lobe width is inversely proportional to the window length. And so we already talked about that. So more time detail means the window length is small. So remember, if n is the number of points, 2 pi over n was the rectangular main lobe width, actually 4 pi over n, 2 pi over n to the left and 2 pi over n to the right. And so if the time resolution is good, you pick a small window, large main lobe width, frequency spectrum is blurry or less frequency detail. And so what that then suggests is the uncertainty principle, which states that you can never have infinite resolution in time and infinite resolution in frequency at the same time. So the product of the time resolution and frequency resolution must have a lower bound, which is 1 by 4 pi. So if we want a high time resolution, we have to settle for a poor frequency resolution. If we want very high frequency resolution, that's like taking the Fourier transform or DFT, and that's all the time in this class. We have been talking about high frequency resolution, then the time resolution is poor, and somewhere in between. So to understand what that somewhere in between means, we can continue with our let this slide shows here how if you look at the two plots on the bottom here, one on left and one on right. On the left, we have very nice time resolution. So the time resolution is very small. At every small time width, we can see what is going on, and that means the time resolution is very good. On the right, the width of that window is much longer than the left. That means the time resolution is not as good compared to the left. If you look at the number of frequency resolution levels, on the left there are only 2 levels, on the right there are many levels. So definitely the right one has higher frequency resolution and worse time resolution. On the left we have very high time resolution and weak frequency resolution. And that really in a very nice way relates to wavelets, which gives you many levels of time and frequency resolutions. So if you look at multiple levels of wavelets, all the way down we get decimation by for high frequencies. Think about it. For high frequencies, we get decimation by factor 2. Then the frequency resolution keeps decreasing, and then the time resolution keeps increasing. So that's kind of that is indeed, I don't think we have slides to illustrate, but in a very nice way, the wavelets provide different time scale representations. Okay, let's complete this example that I started in the very beginning, which says that if we have 10 radians per second in 5 seconds, 40 radians per second next 5 seconds, 50 radians per second in next 15 seconds, and 100 radians, 10 hertz, 40 hertz, 50 hertz, 100 hertz, or 200 pi radians per second in the next 5 seconds. So those numbers 10, 40, 50, 100 are in hertz, twice pi, multiplied by hertz will give you the frequency in radians per second. Okay, so those are all in different time domains. So the first 5 seconds, next 5, next 5, next 5 seconds, sampling frequency 400 hertz, 400 samples per second. And the right plot is showing us the spectrum 10, 40, 50, 100 mapped to discrete frequency and their reflections to the left of twice pi. And on the left, you see those time frequency, short time Fourier transform or another form of time frequency plot. I mean, this is also called time frequency plot because the x-axis is time, the y-axis is frequency, and we see that the 0 to 5 seconds we have content 10 hertz and 40 hertz, 50 hertz and 100 hertz. So that's the essence. I mean, that is all the things that we have been talking about in DFT, FFT, DTFT, and all of those things are really the right side plot, and that's very nice frequency resolution, but there is no time resolution because we don't know when those frequencies were present. But on the left, we take the time frequency representation by the short time Fourier transform, and we do see that indeed we can see how the frequencies changed over time, and that we cannot see from the right plot. Okay. Okay, so to illustrate the time frequency on the time resolution and frequency resolution uncertainty principle, so we take the same signal, xt after sampled with 400 hertz, xn, and we compute here the short time Fourier transform with different window lengths. And on the top left, the window length is 20 samples. So at a sampling frequency of 400 hertz, the 20 samples would correspond to 20 by 400 or 1 by 20 seconds, and 1 by 20 seconds is 50 millisecond. So if you look at this x-axis, we'll see very nice time resolution. We can see exactly what is going on in 50 milliseconds. But as you can see, the frequency resolution is indeed very poor. If you increase the frequency resolution by factor of 2 and reduce the time resolution by factor of 2, now the window length is 40, and that's 0.1 seconds. So there is some improvement in frequency resolution. Then you increase the frequency resolution by factor 5. The width is now half a second of a window, and then 1 second to the right. And clearly, as you can see, the uncertainty principle states that it is impossible to have very nice time resolution and very nice frequency resolution at the same time. And this is a good illustration of that uncertainty principle. Okay. These are some short time, again, just some real sound, same thing. This is a chirp sound. So that's the sound. And we take the spectrum, and you can see here, well, I mean, you can see that from the right plot at least, you can see that this is a band pass signal, and there is, well, the frequency content seems to be centered around probably about 0.2 pi. But if you look at the left, the short time Fourier transform, it's exactly showing how the frequency changed as time goes on. So initially, in the y-axis, let's see here. Okay, so this is an MP3 sound. So 22 kilohertz, the whole y-axis, 2 times 10 to the power 4, 2.2 times 10 to the power 4, and that's 22 kilohertz. So it looks like little less than, say, about 4 kilohertz. So initially we have content something about 4 kilohertz, but then after about 1 second, let me see if is the volume. Okay, that seems high. Okay, that's fine. So we don't need to increase that. So, and then the frequency increases, well, more between 1 second to 2.5 seconds. So this is another sound, creaking door sound. And that's over a 4-second period. And you can see exactly how the frequency is changing with time due to the short time Fourier transform. Let's see, we have a whale sound here. Okay. Again, you can see very interesting short time Fourier transform. It's telling us a lot. If you are going to do sound identification, and that's a whole area of research by itself, and there are numerous scientists, well, their whole lifetime research is on bird sounds. So there is a whole center in Cornell University. I'm not sure if I gave you a sound to play with in early homeworks, but they go to all kinds of places all over the world to uniquely study the sounds of many different birds. And again, you take the spectrogram and the short time Fourier transform, also called spectrogram, and you see how these sounds differ from bird to bird. What is this sound? Okay, this is probably exam coming to an end. Okay, that's well, some kind of a sound. So anyway, so I will post this on your website as soon as this is a digital Doppler ultrasound. And the spectrogram is very interesting, very interesting. This is 25 seconds. So lots of low frequency content all around. Certainly a lot of change as time goes on in high frequency content. Very interesting, and so I'll put the code as well if some of you want to play with it. So let's see, 10:06. Okay. So I will post this on your website, so you will have a copy of these slides. I want to get to those. Okay, let's just see at least. I posted on the handout section of the Moodle site this link to 2D FFT. Very interesting. Look at Yao's slides. I like her slides because she has done a great job in putting together a nice, very nice introduction to 2D FFT, both mathematically as well as visually, and I like the way she has presented. So look at her slides, and some of you may know that the so-called Polytechnic merged with NYU, New York University, and now it's no longer Polytechnic, now NYU, and also known as Tandon School of Engineering after Tandon. Someone who came from India gave $100 million to NYU, and now the school is named as Tandon School of Engineering. Well, it's always nice when schools are named after benefactors. Well, the universities are always looking for funding. Well, we are always looking for a couple of you from this class to become billionaires, so you can give $100 million to the university. Who knows? Maybe someday our College of Science and Engineering may be named after somebody who donates $50 to $100 million. Well, that's kind of price. There is a price for everything. There is a price tag for everything. You want a building named after you, that's probably $10 million. If you want a college named after you, that's somewhere between $50 to $100 million. Well, there is a price tag. You can buy everything if you have the money. Okay. Okay, look at those slides. Let's see. The sample exams. So I listed here the fall 2012 review problem 1 and 2, and fall 2013 the problem 2 is on analog filter design, so don't look at that. So that should actually be very good review for in combination with homework for the midterm exam, and we'll spend a little time on few problems from your textbook, but let's see. So before I work out a few more problems, we'll try to post the last homework solution by tomorrow about 10 o'clock in the morning. So of course you work out the part A and part B, and there is no reason to believe you won't work it out. Any thoughts about this last part? Comment on input-output relationships. Any idea what really is happening in this so-called building block? Yes?
You have a delay and a flip of the outputs, the inputs.
Delay and flip. Okay. Well, let's try to see what is going on, and maybe I won't work out the math part, but let's try to see, and that might be a good way for us to get to our problems. Okay, so let's say, so we have, this is okay, so let's say that these signals are X1 is A1, A2, A3, A4, etc. And this is B1, B2, B3, B4, etc. So after I insert a 0, these become A1 0, A2 0. Example here. Same thing, B1 0, B2 0, B3 0. You delay by one sample, and if you delay that by one sample, so A1, which was available in clock cycle 0, now is available after one clock cycle, that's clock cycle 1. So this will be 0, A1, 0, A2, etc. And if you look at adding these here, so we get what we get here is B1 plus 0, 0 plus A1, B2 plus 0. So anytime you have an expander and a D, and that's kind of, the intent is to tell you that at no point in time, both of them are non-zero. There is no point in time. At any point in time, one of them is 0. And I tried to explain to you that in block diagrams like this, you see something being added, but that's really a dummy adder. There is nothing being added. So this adder is a dummy adder. There is nothing at all being added. Okay? So this is really equivalent to x1 expanded by factor 2, x2 expanded by factor 2, and a switch that switches, well, in this case, as we see, in even clock cycles, we switch to the bottom, and in odd clock cycles, we switch to the top. And that's what is WN. So there is nothing being added. We are just sampling in a ping pong manner. We are sampling here, 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 like that. So sample B1, then B1, then A1, B2, and A2. So, okay, that's kind of what I want you to understand intuitively. Now, all the math is there. I mean, that's all very good. But what really is going on is this whole thing here. This part of the block diagram is known as a parallel to serial converter. So if you are implementing integrated circuits, then you would call that a parallel to serial converter. We have two parallel signals, and then we basically multiplex them, and that's what we also known as the multiplexer. And it's very, so okay, well, I mean, if you are going to be having any kind of multiplexing became a very common thing in communication systems. In fact, I should give quite a lot of credit to Maurice Belanger in France, who did pioneering work on all of these multiplexers in communication systems, applying all the multi-rate concepts. And today, multi-rate multiplexing is part of any, well, in context of IC chips, it's pretty common in any kind of, if you go to the marketplace and buy a chip that has many channels of electrodes, EEG electrodes, for example, and that multiplexes first. So if you get a 64-channel EEG cap, it's collecting all those 64 signals and then multiplexes them, then transmits that to the outer world for further processing or whatever. Okay, so multiplexing is a very common thing, and this kind of a block diagram is describing one simple example of multiplexer, which is parallel to serial converter, taking many parallel signals and multiplexing them to a serial signal. Is that clearer? Okay. So the right part of that is the serial to parallel converter. So if we go back to the same block diagram, so what W1 shows is a multiplexed version of X1 and X2, and then we take the delay one time and then downsample, and then we get back the two streams, Y1 and Y2. Okay, so so which one is Y1 showing us X2 or is showing us? By the way, I should say this is time domain multiplexing as opposed to the frequency division multiplexing in your midterm exam 1. So same multiplexing idea. You can multiplex in time domain, you can multiplex in frequency domain. In fact, all this multiplexing forms the basis of all the third generation wireless systems in 90s that called TDMA, time division multiple access, and the frequency division multiple access, FDMA, and the so-called CDMA, code division multiplexers, instead of relying on multiplexing in time domain, allocating time slots to users, or in frequency domain, allocating frequency bands to users. Code division multiplexers has set of orthogonal codes that form another basis function, just like the complex exponentials form a basis function. Those are orthogonal functions. So if you can design more orthogonal codes, assign, if I have 100 orthogonal codes, I assign them to 100 users. Well, that's essentially, in very primitive explanation, what CDMA is, code division multiplexers. You can take semester courses on each of these topics. Okay, so anyway, so well, let's see what actually the parallel. Let's see, we have about half an hour. Okay, so if I take this, so what exactly is being demultiplexed? So if I call that demultiplexer, or serial to parallel, I should say, okay, parallel to serial converter, also called multiplexer. So if I take this multiplexed signal and then downsample this, well, we get back B1, B2, etc. Delay that by one sample, so this becomes 0, B1, A1, B2, and then downsample by factor 2, so you keep 0 through B1, keep A1, so this is 0, A1, A2. So after demultiplexing, because of the delay, the one that has a delay would really be x1. So that's x1. So x1 was A1, A2, A1, A2 is here, and then B1, B2, x2 is here. So multiplexer, demultiplexer, also known as a serial to parallel converter. Primitive concepts, very primitive concepts, but the applications are numerous and very practical, and there are really, well, literally billions of dollars of chips being sold using these very primitive ideas. Okay, well, I'm trying to put them into basic small principles, small examples, but the implications are profound. Okay, so let me go through a few examples from your book. So let's see. So familiarize with the noble identities that we talked about. So anyway, that's kind of, we need to use those things. So the first problem that I intended to work out is 443. Okay. So let's look at this problem here. Okay. So it says that we want to design a block diagram of an equivalent system that consists of a cascade of LTI systems, compressor blocks and expander blocks, which results in the minimum number of multiplications per output sample. Okay, so so in this block diagram here, we have an expander downsampler or compressor. Okay, downsampler, compressor are same thing. Filter. Okay. Okay. So the intent then is really to reduce the number of multiplications per output sample, and all the so when you think about this kind of block diagram here, because there is nothing being added, and because we are either sampling this or that, that means we are able to reduce the number of computations per output sample. Okay, so let's see how we can work that problem out. So, okay, so the first thing we can do, we can exchange. So these are mutually co-prime. So if I exchange these, we have expander followed by decimator. Okay, so that's our property 3 that we talked about. What about if I want to exchange these, what should I do? Well, what does noble identity say? Noble identity says if we have filter followed by downsampler, that's z to power m goes to the right. So z squared gets replaced by z. So z to power minus 3. So z squared gets replaced by z. 7 plus z to power minus 3 minus 2 z to power minus 6. Okay, well, okay, so now these are again mutually co-prime. So if I switch them, exchange them, well, let's see. Okay, let's leave it. No, let's leave it like that for now. We may have a way of getting around, but let's see. Let's leave it for now. Okay, so
Quick question.
yeah, actually I do. Yeah, let me switch them and then we will. Yeah, go ahead.
You changed the up and down samplers between your 2 steps, like the
first to the second step.
Yeah, it went from up sample 3 to down sample 3.
Up sample 3. Oh, I made a mistake. Okay, well, okay, yeah, that probably explains why I was not sure how to. Okay, thank you. So okay, so that's good. In fact, that's I was hesitant to see what is going on. Okay, so actually now I want to switch them. Okay, so we can see why I was hesitant because there was no benefit to. The only benefit I get now is to combine them as one downsampler by factor 4. I couldn't do that before. because of the mistake. Okay, great. So now this is okay, thank you for pointing that out. So now in fact we have downsampler by factor 4, and now if I go to noble identity number 2, expand by factor L z to power L, okay, then switch those, the z to power L becomes z, z to power L becomes z, so switch these, and then the z to power 3 becomes z, and then this comes to the right, and then expand by factor 3 and factor 3 combined to get 9. Okay, that really completes our problem, and that says that, well, for each output sample, this is expanded by factor 9. I only need 2 multiplication operations, 1 multiply by 2 and 1 multiply by 7. 2 multiplication operations, and 8 of these are zeros. We don't need to worry about those. We are only computing 2 multiplications per output, well, per, okay, either you want to say per output sample as looked at here, or per 9 output samples as looked here. And that's kind of the bare minimum. It has all the very nice properties. We are not filtering using zeros as we were doing here. We have one sample, 2 non-zeros. 2 non-zeros are filtered by this filter. Here we are not computing any sample that we would throw away. We take samples, we throw out what we don't need, then retain those what we need. Those are the only ones that are fed to a filter. So that's kind of what is the minimum number of multiplications. Yes?
So in general, when you want to minimize the number of multiplications, do you want to do all of the compression first, then have the filter in the middle, and then expand?
Yeah, well, I mean, that's kind of a way to think about. I mean, you want to make sure that you are not computing something that's being thrown away. And you are not filtering using zero samples.
Right.
Those
So
are
that's why
two
you don't want to have,
principles.
that expansion before the filter, because
Yes.
then you're just going to multiply by zeros.
Yes, absolutely. Absolutely. Yes. Yes. Yes, indeed. Okay, so that's, so we have 15 more minutes. Okay, so let's see if I can go through one. Maybe I can't go through. Let's go to, it's 458. Very interesting problem. I think that's as you can imagine, a lot of the problems in OpenIM textbook have come from many of his exams. He's turned 80, is still writing textbooks, new textbooks. Is a very handsome teacher and dedicated teacher. Okay, so the problem here states that we have xn upsampled by factor 2, then there is hn, which is a 5-point filter, A, B, C, D, E. Okay, so that's the structure, and that then the problem states that another structure xn is equivalent to that, which is H1 followed by expansion, H2 followed by expansion, and H3 once again very interesting problem, and these are equivalent. Find H1, H2, H3. Okay, that's so. Okay, so first thing we can say, okay, well, we can say, okay, well, so so if you look at HZ, which is A plus B z to power minus 1 plus C z to power minus 2 plus D z to power minus 3 plus E z to power minus 4. So let's, because there are two paths, let me have a polyphase decomposition of H of n. So I can have this followed by the even phase A plus C z to power minus 2 plus E z to power minus 4 followed by the odd phase B z to power minus 1 plus D z to power minus 3 and then add them. Okay, so that's my first step. So decompose H of Z into two polyphase components. Then I can say, okay, well, I mean, I need two expanders. Well, I can say, okay, let's throw that out and put an expander here and put an expander here. Okay, so that same thing. There's nothing lost if I move that expander to all parallel branches, and then I can write this in our factored form: z to power minus 1 plus b d z to power minus 2. Well, that's what it is. And then if I use noble identity number 2 that says expand followed by filter becomes same as filter followed by expand, z to power l replaced by z. So that then suggests that this coming to the left becomes a plus c z to power minus 1 plus e z to power minus 2. So h1n, if I replace z squared by z, push that to the left, that's h1. And here, same thing, b plus d z to power minus 2, push to the left, b plus d z to power minus 1. And we are left with only z to power minus 1. Now, look at it has all the very nice properties that what we have been talking about, and in particular, what I talked about before, here, what I talked about in the beginning, two expanders, one and a lead. That H3n that seemed like a filter and seemed like we would be wasting resources using filtering operation on zeros, indeed has all the nice properties of a multiplexer. This adder is a dummy adder, there is nothing being added. This is a delay element, this is not a general filter, just a simple delay. Two expansions, one followed by a delay, is indeed, this whole thing here is nothing but a parallel to serial converter. So we are taking signal, filtering by the even filter, by the odd filter, and then taking these two parallel outputs and feeding them into a serial output. And that's what this is. Very, very interesting. Any questions about that? Yes.
So the idea that it has to be, that polyphase decomposition has to be used, it just came because there are two parallel paths.
The very essence of this is to waste, to eliminate waste. In the original case, for every output here, we were computing 5 multiplication operations. By pushing the expander to the right, if you look at it, out of every 2 clock cycles, 2 samples. For odd samples, I may be computing 3, for even samples 2. So in 5 multiplications per 2 output samples. So the average number of multiplications per output sample is 2.5, reduced by factor 2 by making sure we are not ever filtering after expansion. Goes back to same idea. Okay. So in general, it so happens to be 5 is an odd number, so it's 5 by 2. But if n was even, number of taps was even, then this would be equally divided. Okay, so let me say there are more ways of even reducing the number of multiplications further that we won't get into in this class. But there are even ways of reducing by so-called fast filter algorithms, and that's not okay. We won't get into that in this class. You have to take probably, well, I mean, certainly if you take my class on VLSI signal processing, we do talk about those kinds of things. It's all about computing DSP systems. I won't teach that until next year spring. So, okay, so that's any other questions? So I think we may have just enough time to work out one problem that I thought we might try to spend some time on. Okay, so that was 4.58. So okay, so this problem here says essentially asking yes or no questions. I mean, it's very simple questions. So the question is saying, are these two equivalent? I mean, there are 3 parts, and in each part, the question is asking, are these equivalent? So, down sample by factor 2 followed by half sample delay, and then z to power minus 1, down sample by factor 2, z to power minus 2. Are they equivalent? Okay, so any thoughts about are they equivalent or not? Okay, so if you think about this, down sample followed by a filter, you can exchange. So I can bring this here, think of this as a filter, then that's equivalent to z to power minus half followed by z to power minus 2, which then is equivalent to down sample by factor 2 z to power minus 2.5. Okay, obviously that's not same because that's down sample by factor 2 half sample delay. This is 2.5 sample delays, so this is not equivalent to okay. While I am at this problem, there is something that I intended to spend a little time on, and that we didn't do that. Is this whole half sample delay. So if we have some kind of a continuous time signal and we have sampled that at some time t, and the half sample delay, if this signal is the input xn, this is x0, x1, and so on, the output would be a half sample delay, which means the output would be these values. Those would be the outputs. So the red ones would be the outputs. This is half sample delay. So how do you implement h of z equal to z to power minus half, which is half sample delay? Any thoughts about this? So remember that, well, what we really want to implement is, if something was defined, it's not, but that's kind of what it would look like. I mean, the Hn would look like something like this. Okay, this is, I just want to make sure you understand, this is not a rigorous notation. Okay, because in a rigorous notation, this has to be an integer, I'm making that half. But that's really, remember that delta n, I'm just trying to put this as an intermediate way to get to the answer, which is sine n pi by n pi. It's 0 for all n, if n is not 0. If n is 0, this is n pi by n pi, which is 1, that's same as delta n. So this hn is really sine n minus half times pi, n minus half times pi. So I just want to throw out my rigorous notation now, by less rigorous notation. So hn, so that's really the filter. That's the ideal filter. And then if you want to design a 11 tap filter, 11 tap fractional delay filter, well then compute n equal to 5 to plus 5 and then shift right by 5. That's, and I might ask these kinds of questions, design a half delay filter. So anyway, I just am trying to tell you that's what I'm expecting. Okay, well, I'm just alluding to a few more concepts. But let's get back to the other two parts and see if we can wrap them up. So the part B says here, there is a z to power minus 1 downsample hn expand and then z. Are these equivalent or not? Okay, so if I write this z to power minus 1, let's try to keep the z here. So this can be written as z times z squared. Okay, so I can then keep the z here. Okay, so then z squared followed by downsampler is downsampler followed by z. So that's downsampler followed by z. And h n is h of z. Okay. Okay, so what is the z transform of h of n plus 1? That's z times h of z. Okay, so if I add these two together, that's z times h of z. So this z is the same, downsample same, these two together, same, expand same, but these are not same. So not equivalent. Yeah.
The first one you wrote z to the minus 1 is equal to z times.
Okay, yeah, I made a mistake. Sorry. Yeah, I am glad you pointed that out. Okay, so that's good. So that's z times z to power minus 2. So that's actually z to power minus 1. So I don't have to go anymore. Well, let's see. Okay, let's try to see what happens here. So this becomes z to power minus 1 h of z. In this one, if I use expand by hz squared and then move that here, so move this here, becomes z to power minus 1. Okay, so then effectively this part here is equivalent to z down sample z to power minus 1 cancel out h, and this here is not going to be okay. Still they are not equivalent. Okay, they are not equivalent because you move this here, this becomes z to power half, and now we have z to power minus 1 times half times h, so the whole thing together is z to power minus half times h, and this is h, and they are not equivalent. Okay, so I think the part C is okay, that's actually trivial, so I think we can stop here. Okay, so this kind of completes the class. The midterm exam will be on content, last part of the content. So see you on Tuesday. You can be our don't go away. If you did not collect your exam key, Chris, Andrew, Catherine, Ashley, Chris, yeah, good. Okay, Ken. So, There is no TA. This is for instructor, not TA. No TA, just class instruction.
So is the exam just material covered by the homeworks, or also like the lecture material today and next Tuesday as well?
Not the parts what I did, not that part. Only the homework.
Just the
That's,
homework.
yeah, I mean, what I talked today is very much in line with the homework.
That
But not the short time for transfer, time frequency uncertainty, not those kinds of things.
okay, thank you.
Sasha, you have one? Huh? Which one? Yeah.
So is there, I just want to make sure that everybody got a form. Is there anybody who did not get a form? All right, see you. Why two students have homework 10 and these are already graded? Yes, the these are already graded, and these are homework 10. And they're